15 billion units, exactly the number of LED light bulbs produced annually across the globe. Why does an industry built on items costing only a few dollars reach a value of over 100 billion US dollars? At first glance, the individual bulb seems insignificant in cost, but the sheer scale of production turns these small lights into a global economic force, illuminating nearly every corner of the planet. But this is just the beginning. The technical journey initiates with a semiconductor chip smaller than a speck of dust. Assembly stages proceed with precision measured strictly down to the micrometer. One can notice how gold wire bonding connects components using threads thinner than a human hair. It gets more complex further on. Color conversion layers are applied to modify the light spectrum. Protective encapsulation seals the delicate electronics against the environment. Large-scale light testing verifies the brightness before the product becomes a source of illumination for the entire world. Chips that are almost invisible are transformed here into billions of functional units. These light sources brighten the planet every single day. More than 100 years marked a period where humanity burned vast energy reserves for minimal brightness. Why did this costly trade-off persist for such a long time? Old incandescent bulbs generated intense heat, while fluorescent lamps depended on glass tubes filled with toxic mercury. The world simply waited for a solution that was cleaner, cooler, and significantly more durable. But this is just the beginning of the transition. LED technology emerged specifically to answer this critical demand. One can notice how early versions served only a supporting role in electronics. At first glance, these faint red indicators on control panels seemed insignificant, but in reality, they held the potential to overthrow the existing infrastructure. However, they lacked the power for general illumination at that stage. The process is only gaining momentum, because a single technical hurdle remains standing in the way. If a blue diode could be created, the combination of colors would finally produce white light. It gets more complex further on. In 1994, Japanese engineer Shuji Nakamura identified the precise semiconductor material required. It is visible how this breakthrough allowed the device to emit light reliably for the first time. Thus, the creation of white light became a physical reality for the industry. A single microscopic particle of dust is enough to irreversibly ruin thousands of future chips at once. Every modern LED lamp begins its existence with a semiconductor chip grown on a crystalline substrate, most commonly sapphire. But before any crystal can be processed, human beings must enter an environment that is almost absolutely clean. The entire manufacturing area operates as a massive clean room where contamination is the enemy. But this is just the beginning. Engineers and technicians are required to change into full protective gear, donning one-piece clean room suits, hoods, masks, gloves, and anti-static footwear. This strict protocol applies to every shift. Why must the personnel pass through high-pressure air showers before entering the main hall? It might seem that the protective suits provide sufficient isolation. However, these showers are designed to strip away any remaining dust or contaminants that could compromise the strict specifications. One can notice how the sapphire substrates are carefully loaded into epitaxial reaction chambers, operating at extremely high temperatures. Masses containing gallium and nitrogen are then introduced into the system. It is visible how the gases flow across the sapphire surface, bonding atom by atom to the base. They crystallize into ultra-thin layers far beyond the limits of human vision. The process is only gaining momentum. At first glance, it seems like a simple coating, but in reality, specialized semiconductor layers are formed and stacked with precise order. This formation creates the critical p-n junction structure, because it is within this junction that charged particles collide when an electric current flows. The reaction releases energy in the form of light. marking the moment the LED is born at the atomic scale. This physics dictates the future efficiency of the lamp. The high-temperature phase concludes here. The material is ready to move to the next processing phase. Millions of semiconductor structures lie hidden beneath the mirror-like surface, formed at the atomic scale. After epitaxial growth, the wafer looks smooth to the naked eye, but these layers cannot yet produce light on their own. To transform them into functional units, the material must undergo the complex process of photolithography. But this is just the beginning. The wafer enters a zone illuminated entirely by controlled yellow light. Why is this specific lighting spectrum necessary? It seems like a standard safety protocol for the facility. In reality, the surface is coated with a light-sensitive photoresist that would be instantly destroyed by the harshness of ordinary white light. Ultraviolet light projects through a precision mask, drawing microscopic patterns with accuracy down to individual micrometers. One can notice how chemical developers wash away the unwanted regions of the coating. This leaves behind an intricate network of ultrafine circuit features on the disc. It gets more complex further on. The process shifts to a vacuum chamber for the next critical phase. An extremely thin layer of metal deposits onto the surface to create electrical contacts. At first glance, this seems like a simple coating, but in reality, it transforms the wafer into a massive light circuit board. The metal evenly covers the microscopic topography to lock in conductivity. Tens of thousands of individual LED chips are thus formed simultaneously, waiting to be separated in the next stage of production. Tens of thousands of identical LED chips lie waiting beneath the mirror-smooth surface of the wafer. This microscopic map is arranged in perfect geometric order, fully formed and simultaneously awaiting the next phase of production. Why is the separation process executed with such extreme caution? To the naked eye, the wafer appears to be a single, solid sheet of material. However, any physical stress during cutting could shatter the internal structures, rendering the work useless. The factory employs a high-energy laser system with extremely precise beam focus to solve this challenge. Guided along pre-calculated scribe lines, the beam cleanly slices the wafer into thousands of tiny square dies. One can notice how the laser glides over the surface, minimizing cracking and residual stress that could otherwise damage the internal components. But this is just the beginning of the precision required. Each individual LED chip measures only a few tenths of a millimeter across, which is smaller than the tip of a needle. Yet inside this speck of matter, a complete light-emitting region, semiconductor layers, and a fully formed PN junction reside. At this scale, even a microscopic fracture is enough to render a chip non-functional. Therefore, the separated units must undergo immediate verification. The LED chips pass through an automated inspection system immediately after cutting. Each chip is briefly powered on to verify that it emits the correct color and operates at the proper voltage. One can notice tiny flashes as the machine tests the grid, ensuring absolute compliance. Defective chips are removed on the spot. Only those that meet all specifications are allowed to continue their journey. At first glance, the cut wafer seems ready for assembly, but in reality, the chips remain firmly attached to a thin carrier film. In this state, robotic systems cannot pick up individual chips with micrometer-level accuracy because they are positioned too closely together. For that reason, the film is fed into a crystal expander machine. It gets more complex further on. Uniform tension is applied from all four directions to change the geometry of the sheet. It is visible how the film stretches outward, gradually separating the chips from one another as the material expands. The spacing between them increases according to pre-calculated dimensions, ensuring there is no distortion. The result is a perfectly ordered chip grid where every die is evenly spaced and precisely aligned for the next machine. The film carrying the separated chips is transferred to an automated pick-and-place system. Thus, the components are fully prepared to enter the die bonding stage without haste. 20 to 30 micrometers. This minuscule distance stands between a functional light source and total failure. The pick-and-place system enters the crucial die bonding stage, where each microscopic light-emitting diode chip is fixed onto a metal lead frame consisting of two terminals, the positive anode and the negative cathode. An automated die bonding machine dispenses a precisely controlled dot of thermally conductive adhesive onto a designated position on the lead frame. This adhesive plays a dual role by securely anchoring the chip in place while also providing an efficient path for heat dissipation. As a result, both the volume of adhesive and its placement must be accurate down to individual micrometers. But this is just the beginning of the assembly. The expanded film carrying the separated chips is then fed into the machine for processing. Why is such rigorous scanning required for every single unit? Industrial vision cameras scan the entire surface, automatically identifying the exact coordinates of each chip, as well as the metal pads on the lead frame. This data allows the system to calculate positional offsets within just a few micrometers, ensuring that every chip is placed with extreme precision. One can notice how the robotic arm operates at near instantaneous speed. Pick up, rotate, align, and place. Each cycle takes only fractions of a millisecond to complete. A gentle downward force is applied to spread the adhesive evenly, preventing air bubbles and ensuring the chip remains perfectly level. At first glance, this mechanical motion seems like simple repetition, but in reality, it is a high-stakes operation where absolute consistency is paramount. Precision at this stage is critical, as a misalignment of just 20 to 30 micrometers can cause color shift, reduce the lifespan of the diode, or even lead to immediate failure in the next processing step. And this is not the limit of the system's duties. For this reason, once an entire strip of chips has been placed, the lead frames are transferred into a thermal curing oven. It is visible how the components enter the chamber where a stable temperature is maintained for several minutes. This controlled environment allows the adhesive to fully cure, permanently locking each chip into position as a unified structure. The bond solidifies, preparing the strip for the next stage without haste. 99% purity is the strict standard for the gold wire used here. The material enters the automatic wire bonding machine only after the LED chip is fully secured to the metal lead frame. Engineers select a wire diameter between 18 and 25 micrometers. One can notice how the filament, 3 to 5 times thinner than a human hair, feeds into the precision mechanism. But this is just the beginning of the microscopic assembly. Why do high-resolution industrial cameras scan each chip with accuracy down to a few micrometers? The components are too small for simple alignment alone. This digital calculation ensures the exact position of the terminals is known before contact is made. Without this data, the connection would fail. Using a mix of heat and ultrasonic energy, the equipment executes the bonding sequence. It is visible how the machine forms a tiny gold ball at the tip and presses it onto the electrode for the first bond point. The wire is then drawn into a carefully shaped arc before being lowered onto the metal lead. It seems like a simple mechanical movement, but in reality, the second bond requires perfect adhesion. The wire is cut, and the head moves to the next unit without pausing. Despite the extremely high speed, every step maintains uncompromising precision regarding loop height and tensile force. This guarantees a reliable electrical connection and long-term stability for the final product. Everything only gets more complicated during quality control. Technicians scrutinize every loop under high magnification microscopes to catch defects. Any LED showing weak bonds is removed immediately. Only fully qualified components proceed to the next stage of production. 1/10,000th of a gram is the precise weight deviation allowed for raw phosphor powder during the initial measurement on an analytical balance. This minuscule amount is equivalent to approximately 0.0015 grains. After the gold wire bonding and inspection stages are completed, the frames move to this coating area where engineers blend yellow, orange, and pink powders. Why is such extreme precision required for a simple powder mix? The process looks like a standard chemical recipe, but without exact ratios, the target color temperature would shift, rendering the entire batch's light output inconsistent. The components enter a high-speed rotary mixer to disperse the powder evenly throughout the liquid epoxy solution. But this is just the beginning of the optical transformation. One can notice how ultrafine dispensing needles of the dotting machine hover over the lead frames, depositing the mixture onto each individual chip. The volume is consistent down to millionths of a liter, or approximately 0.00003 fluid ounces. Thousands of units pass through the chamber as the liquid covers the semiconductor with absolute uniformity. It seems obvious that an LED bulb naturally shines white, but in reality, the semiconductor chip always produces a native blue emission. It is the yellow phosphor layer that intercepts this blue light and converts it into the white or amber spectrum visible to the human eye. To lock this chemical reaction in place, the trays enter a curing oven operating at approximately 302 degrees Fahrenheit. The heat hardens the epoxy, creating a permanent optical surface across every unit. It gets more complex further on. The strip transfers to the epoxy molding area to finally receive its signature transparent lens. Liquid epoxy resin is injected into steel molds containing hundreds of precisely shaped cavities. These forms dictate whether the final unit will have a 5mm round head, a flat top, or an oval lens. It is visible how the viscous fluid fills every void, preparing to define the shape of the light. Therefore, the filled molds are moved into a circulating thermal oven operating between 248 and 302 degrees Fahrenheit. Under this controlled heat, the material undergoes molecular cross-linking, gradually transforming from a viscous liquid into a solid, crystal-clear structure. When the cycle concludes, the LEDs are released from the mold, revealing a rigid plastic lens that fully encapsulates the chip and gold wires. The metal leads extend cleanly from the base, marking the completion of the protective housing. Hundreds of individual lamps are defined by the requirement that the molded form needs extending cleanly from the base. Once the epoxy has fully cured, the steel mold is open, revealing a long LED strip containing the lamps. One can notice the units appearing nearly finished, yet all still remain connected together on a single metal lead frame. But this is just the beginning. At this stage, the product is still only a semi-finished component. Why do operators perform a quick visual inspection of each strip? The automation waits. This step is necessary to ensure there are no molding defects before the mechanical separation begins. The LED strip is then fed into a deframing machine where a system of precision, aligned cutting blades and metal punching mechanisms operates with extremely high accuracy. At first glance, the impact seems forceful, but in reality, the thin tie bars linking the LEDs are cleanly cut without damaging the housing. In just a matter of seconds, the blades complete the cycle. The process is only gaining momentum. The mechanism releases each LED package as an individual unit. It is visible how the components are precisely formed to their standard dimensions. From here, the separated parts transition to the next phase of the production line. Microseconds are all it takes for the automated electro-optical testing system to activate each unit after it is separated from the metal frame. Why is such precise individual inspection necessary for millions of components? To an observer, the batches already appear identical after the initial formation to standard dimensions. But without this step, slight variations would cause visible inconsistencies in the final product, rendering the batch unusable. But this is just the beginning. One can notice how the LED is powered on and illuminated in a brief instant for the sensors to react. Industrial cameras and optical sensors measure operating voltage, color output, and brightness with absolute precision. At first glance, the light appears uniform, but in reality, the equipment detects subtle deviations in color temperature that the human eye cannot detect. The process is only gaining momentum. The binning system immediately utilizes this collected measurement data to sort every component into distinct groups. Pneumatic mechanisms rapidly direct each LED into its corresponding compartment based on specific electrical voltage and brightness levels. It is visible how the sorting machinery isolates units to ensure they emit uniform light without color shifts when later assembled into a light strip or lighting panel. Everything only gets more complicated. From here, the qualified components move directly to the lead forming and wire handling stage. Metal leads are shaped, aligned, and secured on specialized conveyor systems to prepare the units for downstream assembly. One can see the successful LEDs being carefully dried and sealed in moisture-resistant bags or trays to prevent environmental damage. Labels with batch codes, binning data, and production dates are applied before the finished shipments are secured. Factories worldwide receive these parts for electronic devices, displays, and toys, ready for the final delivery to consumers. Countless diodes make LED lighting an indispensable part of modern life. Why use such meticulously engineered manufacturing processes? It seems excessive. But familiar materials require strict precision to function correctly. It does not end here. At first glance, the result is simple, but in reality, the industrial world operates down to the smallest details. One can notice the uniform structure of the components. The engineering cycle is complete.